Thank you very much. That was, makes me blush a bit. I'm very happy to be back. I was reminded I was actually here 20 years ago, and I'm very happy to be back and see how the place has blossomed. So I'm going to be talking about adhesion, friction, and lubrication of surfaces, liquid films, and the relationship to diverse phenomena, meaning everyday phenomena. The study of friction is very old, and here's a section from my book on the section on friction, and it says that there are 3 laws of friction, and they're all wrong, and also attributed to the wrong person. It was actually Leonardo da Vinci who did some of the early experiments. The 3 laws of friction are that the friction force is proportional to the load. Well, that's totally wrong. You can have friction even if there's no load. If things stick, you can't slide them usually. So what's this thing about the friction force being proportional to the load? It's independent of the area of contact. Well, that was in the days when they just did experiments with bits of wood, and if they put the wood on one side or on the other side, they didn't look at molecularly smooth surfaces. As soon as you do that, then everything changes. The third one is a kinetic friction, which means the friction when things are moving rather than at rest, which is called a static friction, is independent of the sliding velocity. Well, that too, in the olden days, they just looked at the range of velocities, maybe a factor of 10 or even just a factor of 3, so no difference, and concluded it, they just took some old bits of wood or dried skulls or bones and just slid them on something. Like here is Leonardo da Vinci's experiments on friction, and that's the way that they changed the load, the velocity, and so on, and made these 3 conclusions, which are known as Amonton's laws, even though it was Leonardo da Vinci who actually did the experiments. Now, interestingly, actually I was in Florence just a few weeks ago, and I was looking at the Leonardo Museum to see this device, and I couldn't find it. They had all sorts of devices. Leonardo da Vinci was an amazing person. He made drawings of almost anything you can think of, including submarines and tanks. None of them were built. A few of his flapping, making people fly were built, unfortunately, because people tried them jumping from the spires, one spire ending up hitting another spire in Florence. But he was quite amazing. And, but anyway, the important thing when it comes to friction is that there's a dead load here. The load doesn't change, whereas usually when we have friction, we have something being pushed by a spring. And that makes a total difference to what happens. Here, the load doesn't change the way you do it, or if you tilt something and see it sliding, basically the gravity or that's pulling it doesn't change. But if you're pushing something with a spring, then everything changes, because as soon as the thing you're pushing moves, the spring then reacts. And that really changes the whole field of what happens. I'm going to be describing some results using various experiments, many of them using a Surface Forces Apparatus. And as you heard, this is one of these apparatus that I was fortunate enough to be involved in its design. And I won't go through it in any detail. I'll just say that the surfaces are here, the extended surfaces, and everything else is just mechanisms of springs and piezoelectric crystals and more springs for measuring, for displacing the surfaces over distances from millimeters to contact with 1 angstrom resolution. And this chamber is then filled with liquid. You get a feel for the size of it. So these are macroscopic surfaces. The contact area is typically many microns to a millimeter. But the important part of it is that there's a light beam that's driven through the surfaces in order to look at them. And this uses the interference technique, multiple beam interferometry, where white light is passed through the surfaces, and it's white light, and there is multiple reflections as the light passes through the two surfaces. So when it gets separated by a spectrometer into fringes, you see beautiful fringes in color that reflect exactly the shape of the surfaces and also the distance between them. I don't have time to go through this, but let me just say that if you've got two surfaces close together, maybe 10 nanometers, with two mica sheets, which are often used, silvered on the back, and light through it, one will see parabolic-like fringes that give the exact shapes of the surfaces. And the position of the tips is the position of closest approach. When the surfaces are brought together, if they adhere, they will suddenly flatten as the adhesion causes them to deform and flatten, and one can then see the contact area. If there's some liquid between the surfaces, there's a meniscus, and you see discontinuities in the fringes. Whereas if you look at it just from the top with an ordinary microscope, you will just see a circle of a liquid droplet. So this technique has been around for quite a long time, and most of the results I'll show, or some of them will be obtained using this Surface Forces Apparatus method. It's sort of similar. There are many other methods used for measuring forces, including friction forces. Oh, I should say that one can also move the surfaces laterally and measure friction forces as well as normal adhesion forces. The Airframe is another well-known technique where one can also have a spring and a tip, in this case, instead of two surfaces on a surface. And by scanning it one way and the other, one can also measure normal and lateral forces, and in this way get information of interactions of very small tips or molecules with surfaces. So that these two techniques, in a way, are complementary. The interaction of a molecule with the surface can be quite different from the interaction between two surfaces, extended surfaces. So there are many other techniques one uses as well in trying to get a full picture of how surfaces interact in liquids or in vapors. The first thing I want to do is just give a very simple background to adhesion and its relation to friction. Adhesion is the normal force needed to separate two surfaces. You bring them together, you separate them. Friction is the force you need to push laterally surfaces past each other. Now, whenever you bring two surfaces together, there is what's known as the surface energy. And if the process is thermodynamically reversible, the surface energy is, by convention, half of the work of adhesion. That energy that you gain when they adhere should be exactly the same as the energy you have to put on separation. So A for attraction or approach, R for retraction or receding. So gamma R or WR, if it's a work of adhesion, will always be greater than that. Thermodynamically, you cannot have a perpetual motion machine. So in practice, either it's identical, they're the same, in which case the system is totally reversible, or it's not. And if it's not, you get what's known as adhesion hysteresis. And this is typically what happens. It's related to friction in a simple way, because when you slide surfaces, they're doing much the same as here. They're sort of going up a bit. Some of the bonds are broken, but not all, like here. But then it goes down again, and then they're made. So you have the same process going on. You're breaking bonds, and then you're making them again, and breaking and making. So it's very easy to write a very simple equation, which works very well in simple cases where we have no liquid, no lubricant, nothing complicated, that the friction force times the characteristic distance, which is an atomic one, will be twice the area, twice because the gamma is half of the work or the energy. The difference in that multiplied by epsilon, which is the fudge factor, which will tell you what fraction of the energy is actually transmitted on each collision. This is something that only computer simulations and experiments can establish. But epsilon is often very close to 1, which means it's like a billiard ball hitting another billiard ball. As soon as it hits it, If it's the same mass, the first billiard ball will come to a stop, and the second one will carry on it all the energy. These are things that actually computer simulations in the 1980s revealed for the first time, which it was very difficult to do modeling of friction processes at the molecular level until computer simulations came along and showed the subtleties of what goes on when you have many particles on one surface interacting with many particles or molecules of another surface. This table shows a summary of a number of different experiments, but basically showing how the friction force scales with the load in an ideal case, where you have some adhesion. And here's the contact area that I was mentioning before. You can see from the fringes, the real contact area. At zero load, there's already a finite area of contact because the surfaces deform in order to come together. And then you increase it. It follows very nicely what's known as the Johnson-Kendall-Roberts theory. You'll notice that as you separate, you get a negative force. This is the adhesion force needed to separate the surfaces, where they jump apart or spontaneously separate. As soon as surfaces get damaged, you get Hamilton's law. Here, the friction coefficient is you can't talk about a friction coefficient in the sense of the friction divided by the load, which is the traditional definition. Well, still is, because here you get infinity, and it's not a constant. So the idea that it's a constant is clearly not correct for molecularly smooth surfaces. You can talk about the force as a function of load, but not a friction coefficient, unless you use the slope, and even then it's not that convenient. But as soon as damage occurs, you get a nice straight line passing through the origin. Likewise, if you look at the same surfaces in a solution of water which lubricates them, the friction is very low. But as soon as damage occurs, you get exactly the same friction coefficient, meaning damaged surfaces are a hodgepodge of flakes and debris particles and so on, and they are now determining the friction force, and this is known as load-dominated, load-controlled friction as opposed to adhesion-controlled friction. Because now when you move the surfaces, they have to overcome the normal load, and that's given by a certain fraction, is the tangent of the angle. It's like pushing a cart over cobblestones. You double the load, you'll just double the amount of force you need to push them over that. That's the simplest way of looking at it and is apparently correct. Here are similar results obtained using an AFM, where the magnitudes of everything are very different. The radius of a tip is very much smaller than the radius of the surfaces used in a surface forces apparatus. Here they're typically nanometers as opposed to centimeters. The pressures are different, everything's different, and yet one gets very similar behavior. You start off with something that has adhesion, has this curvature, and as you continue going back and forth scanning, you get damage forming, and this is slowly tending towards a straight line passing through the origin that will give you Hamilton's law. The issue of velocity and dynamics is extremely important, and this is what I want to talk about next. There's something known as the Streiber curve, which is also something used a lot by tribologists. Actually, I should mention it's a bit unfortunate about friction coefficients, because since it's been around for so long, there are even laws that have been passed that a floor must have a certain friction coefficient. If it's less than that, then if someone slips, then they can sue whoever it is did it. And that's silly. It's worse than silly. There is no such thing as a friction coefficient that belongs. People thought a friction coefficient was some property of a surface, like its surface energy or density or some thermodynamic quantity at one time, irrespective of what the other surface was. Then there was an observation first made by a German. I don't know, everyone always seems to get the wrong name, and then still named after Streiber, where it was noticed that if you have lubricated systems, you get the friction force or friction coefficient increases with the velocity as you would expect for a viscous liquid, just due to co-ed flow, for example. But then at lower velocities, it goes up, and then sort of nobody quite knows what happens. This is a very rough curve. As you can see, the idea was that things at high velocity slide with liquid between them, and as you go slower, they come into contact, and so the friction goes up. But it was also in terms of parameters that turn out to be, when one looks at it in detail, one realizes that none of these parameters really should be there. The assumption that the bulk viscosity is the same in a thin film is totally wrong. Anyway, I'm just presenting what is often used in interpreting results. Now, it was shown using a number of different experimental techniques. Here I'm showing some results with the Surface Forces Apparatus, that if you measure the viscosity of a liquid as a function of the shear rate, and you bring the surfaces closer together, and this could be any liquid except for water between hydrophobic surfaces where things are different, but any liquid between two surfaces, or a polymer liquid or a polymer melt, if the distance between the surfaces is large, and by large it would be more than 30 nanometers in this particular case, but in other cases it could be just 5 nanometers if it's a smaller liquid. You notice lots of orders of magnitudes here. Then at these distances of shearing, you get the bulk viscosity. It doesn't matter what speed you go. But as soon as you go much closer, everything changes. And as you go closer, at lower speeds, you get this increase in the viscosity. And that's actually the reason why the Streiber curve has, in most cases, this upturn, not because of contacts being made. Even though contacts may be made, it's usually because in a very thin film, a liquid is jammed, the molecules are jammed, and the viscosity goes up and can go up by many orders of magnitude. What happens eventually as the shear rate goes to 0? I will come to in a moment. Nobody quite knew what happens there because you need to go to very low shear rates. So what is the effect of shear rate? Well, on viscosity, there's a well-known experiment known as the pitch drop experiment, which I think is the second longest experiment that I'm aware of that's still going on. If you take pitch and you hit it with a hammer, it breaks like a brittle solid. And if you're a material scientist, you will say it's broken like a brittle solid. If you put those blocks in a funnel and come back a year later, they won't look much different. But if you come back 10 years later, you'll see that it started to flow and has formed a droplet, and the droplet falls. This experiment started in 1930. It's still going on in Queensland, Australia. These are the years where each drop fell. This is a perfectly viscous liquid. It's just, just takes time. What's the rush? Unfortunately, they introduced air conditioning, and now by increasing temperature a few degrees, decreasing it, it now takes much longer, 2 years. So now it takes 13 years instead of 9 or so years. But this is an example that's actually very important. The viscosity can change by orders of magnitude, not only, or rather, first of all, the viscosity can be very high. So the rate at which you do things is very, very important. And in engineering timescales, we do have to consider, if we're doing biology or something else, things moving at high speeds, 20 meters a second if you've got engines, but maybe 20 nanometers a second if you're looking at earthquakes. And in each case, there's friction. And in biology, it can be also a large range of velocities and distances between the surfaces. One of the implications of a Streiber curve, let me just go back again to a Streiber curve is a negative friction force means you're going to get stick-slip friction. If you're measuring or if you have a system which uses a spring in order to move the surfaces, which is what happens usually, or a compliant element. Because as soon as you reach the maximum, the surfaces start to move, and then the friction falls, and then they accelerate, and they continue accelerating until the spring gets extended, and then they decelerate, and then it stops, and then it starts again. So stick-slip friction is very common. In fact, I would almost say that every time you have friction, there's stick-slip at some frequency and some amplitude. This is an example of very regular stick-slip between two surfaces with 2 or 3 layers of highly ordered molecules. This is stick-slip. And there's almost always a critical velocity above which the stick-slip disappears. Because now the surfaces are moving so fast when they slip that there's no time for them to rearrange in order to stick. Very often what happens is you get very regular stick-slip, and then as you increase the velocity, the amplitude falls, the frequency goes up, and then it becomes what's known as chaotic. And I'll give examples of this. This is the sort of thing that happens with earthquakes. In other cases, you just get what looks like, as you increase the velocity as a function of time, you just get it saturating, and this then obeys the laws of Couette flow, can be described by a viscous force between two shearing surfaces. However, there's always little patterns there, and often they are ignored, but when looked at carefully, they actually are not noise, they actually are real effects, and I'll come to that later or pretty soon. Now, an example of this stick-slip effect, here's some experiments that were done a few years ago by some very good postdocs and students I had. Once again, you see, you do need to look at many orders of magnitude of velocity, here measuring the force, the friction force, to see changes. And one thing you notice, when the slope was negative, that's when there was stick-slip. Then it goes positive again. This is a Streiber curve. But the reason for it is different, but still the manifestation is that one of the effects, and that's what wasn't appreciated by, for example, Streiber or Leonardo da Vinci or Amantons or the people who created those laws of friction, because they used a constant load, a dead load, where you can't see stick-slip. Once it slips, it continues, and that's it. But in practice, there's almost always stick-slip. The other thing is that if you go to 0 velocity, you could even demonstrate theoretically at a finite temperature, the friction always has eventually to go to 0. If you give something an infinite amount of time to relax, at a finite temperature, no matter what the system is, it will always move, albeit, however, slowly. It might take the age of the universe, but it will move under the slightest force as the vacancies, atomic vacancies in the material get replaced by molecules, preferentially those that are pushing it in the direction that the material is being strained. Whereas in more realistic systems, or in other systems, in this case 2 bilayers in water, you can actually see this already happening. But still, these are quite low velocities. Here we're talking about 10 to the minus 4 microns a second, so that's getting to less than nanometers a second. Now, why am I saying stick-slip is important? Because there's so many phenomena where it comes in. So just measuring a friction force or coefficient of friction really isn't enough to get a complete picture of what's happening. And I'll just give you some examples of stick-slip. And I'll start with just this one because it's sort of biological and one wouldn't expect that. The way that leukocytes go over endothelial cells, have been measured, and those that are in contact with them, they interact through ligand-receptor bonds. And people have measured, this is work by Dan Hammer done some time ago, multiple ligand-receptor interactions, make and break bonds. And this is the way the immune system works in the search for foreign bodies. Now what happens is basically if you follow the cells, you find a particular cell, it'll stick for a certain time, and then it'll slip, and then this is sticking again if you wish. Here it's slipping, and it's about to go into the bulk. The bulk would be 200 to 800 microns a second. This is only 4 or 5. It still sticks, so meaning it's creeping, it's sticking, and then eventually it detaches completely. All this is actually, nature has developed a system where somehow this is critical for recognizing, this is the way that it's like a bus that stops and then picks up passengers, or it stops and goes, and very clever way of actually detecting things. Now, if I have time, which I don't, was going to talk about squeaking doors. A squeaking door is another example of stick slip. But now think of the frequency. The fact that we can hear it, it's about 10 or 20,000 hertz. And the amount of jumps is very, very small. It's maybe a micron. But yet we hear it loud and clear. And if what we would do subconsciously to get rid of it, we'd open it much faster. And then it doesn't, then the squeak goes away. There's always a velocity range at which it happens. I was once asked by Kimberly Clark, they have a problem with diapers, which work by Velcro. And when they rip it open, it wakes up the baby, and the baby starts crying, and how can we stop this friction from making this sound? So I said, well, it's a nice example of stick-slip friction. We've got to devise a system where when you pull it, it doesn't make a noise, doesn't have a high frequency, it just comes off in one go. And we worked on that. You never know whether you solve a company problem. If they invite you again for a while, that means that they think you are helping them. But when they stop, you don't know whether they think you're a total waste of time or you saved them $100 million. So I don't know. But I made a suggestion that they concentrate not on the Velcro, but on the backing material, make it stiffer, and then according to theory, it should just come off in one go. And this is called stiction, where you get just a single stick-slip spike that can be quite large, and that often causes damage. Crashing computers. In the olden days, IBM would tell people, don't shut off your computer. The disk goes round, and the head flies on top of it, doesn't touch it. As soon as it stops, you turn it off, the head goes down, and then when you start it again, you get a very massive friction force, which is known as stiction, and that's when the damage is caused. In fact, chocolate and mayonnaise, yes. The different food has two sensations occur with food. One is chemical, and one is physical, known as mouthfeel or texture. The chemical part is easy to understand. It's basically what sort of things are coming into contact with your chemical sensory taste buds. But the physical one is really to do with how crunchy it is. And very often, food, especially things like chocolate and mayonnaise and many other things, the difference between what people like and people don't like is entirely due to the stick slip. And again, it's at high frequencies. If you grind your teeth, you can hear it. If you rub your fingers, you can hear it. That means that things are happening at the hundreds or thousands of hertz regime and not just low frequencies. Violins. The reason we can hear a violin is because of stick slip and music in general, sound. And here is a test for everybody here, and the answer will be given at the end of the lecture. And those who pass can get the drinks. Those who don't, they get punished, no? They have to pay a fine. Anyway, so here's 3 violins. I'm not saying which is which. One is a Stradivarius violin. One is a very good violin. and one is something from Kmart. And you've got to decide, just by looking at the resonance, all of these are the frequencies that will come from those violins, which is to do with the resonances due to just sliding the bow at constant velocity, and yet you get all of this sound coming out. So you can work that out. And a little bit more on stick slip. We did some experiments with cartilage in the Surface Forces Apparatus, and we found that there was a certain regime of velocity where the friction forces had this Streiber curve look. They go up, down, and up. And depending on the load, we would be in different regimes. The higher loads would be there. And interestingly enough, it was always in this regime where we would see damage. So even in biological systems, even though, oh, and we could tell that there was stick slip. We measured small stick slip spikes, or even though they're small amplitude, maybe high frequency, they are causing damage. So things at small amplitudes, of course, in the biological world, 10 nanometers isn't small. If you're dealing with tissues that may have delicate membranes, 10 nanometers or so is big. And yet another example, earthquakes. People who have been working on earthquakes for a long time used theories which were totally sort of unrelated to friction. And then recently, or at least in the last 15 years, it was realized that the theories that people who are working on seismic effects and earthquakes and things like that were using exactly the same ideas and theories and models that people in friction were. So, of course, with earthquakes, things can go either towards each other and go up. They can slide sideways. They can go up. Each of them is an example of friction. And here's some experimental results showing the power spectrum is a function of frequency in cases where there's stick slip between two surfaces, where the friction is, as I mentioned before, chaotic, where it seems to be all over the place. But you think it's noise, but it isn't. It's not noise because you can do a power spectrum and you find that it follows, the frequency and amplitude are correlated in a way that shows that it's chaotic. The difference between chaotic and random means it's totally unpredictable. Chaotic means it's in principle predictable. Not that you can predict it or that we know how to predict it, but it is predictable. Essentially, these are things that mathematicians call the Lyapunov exponents also, that it means that there is some sort of connection between them. They're not random. And same with earthquakes. This is exactly the same type of plot. And they follow also something that has a similar type of power spectrum to friction. This is particularly nice. And these are all theories by people who work on earthquakes that got together with some of the friction people to see that, oh, well, we're doing the same. We're doing the same thing. Another example, finally, is to do with a new attachment that, oh, forget about this. I just came from a DOE conference where I showed this. What did it say? Next promising step. They asked me to show promising experiments I want to do in the future. So I put promising. Study extreme conditions of friction. Yes, putting basically a disk in, so now one can go to speeds of up to 20 meters a second. The Surface Forces Apparatus that I was showing before, also AFMs, really, they don't go very fast. They go maybe up to 100 microns a second or so, maybe a millimeter a second. But many systems, you want to go to much higher velocities. When we walk, I mean, the body, engines, so on. And then you find that there can be a number of regimes that have stick slip. At one frequency regime, it'll have stick slip, then it'll be smooth sliding or apparently smooth, and then a different one. And as an example, I'm going to show some things that we have measured, which is essentially what our sensory cells detect when we rub our face or the skin and what we feel, what the signals that are generated, that are sent to the brain, that gives us how it feels like, which we're trying to mimic, trying to see if we can measure and then correlate it with what the real sensations are, like I said, mouth feel and so on. There's a pattern here, and obviously there's at least two different patterns. There's a high frequency and then a low frequency thing. The brain will actually make use of that and somehow process it in a particular way. But one of the things that many companies would like to do is to make a product and to know whether it's going to be successful, not by having people test it or putting it on the shops, on the shelves, and then finding it sells or doesn't sell, but have a machine that can measure something and tell them, yes, this is a winner. No, this is no good. And by measuring all these subtle effects for things like creams and shampoos and conditioners and fabric softeners and cosmetics and food might one day lead to it. But then interestingly, you can go to then a very high frequency or a different frequency, and then you see something totally different. Stick slip always has certain spikes, sawtooth-like. But sometimes you see sinusoidal things. And it looks like stick slip. There's a different frequency regime where you get that. But that isn't due to stick slip. It's not a lubrication thing anymore. You're now triggering one of the resonant frequencies of the apparatus, of the machine. If it's a car, when you engage the clutch or the brake, unless it's automatic or self-drive, in which case you're not there, it often has shudder or chatter or vibrations. So these are vibrations that may appear like stick slip, but actually it's more of a resonant resonant triggering, high-frequency resonant vibrations. So when you change velocities by a large range or loads, you can get a whole series of very interesting results, each manifesting different phenomena. Finally, I want to talk about geckos a little bit, and then just a little bit about liquids. How do we do it? How do they do what? Well, there's 850 species. They can climb on walls and ceilings. They can climb very rapidly. Oh, I was going to ask Bosun to get me some sellotape because I wanted to do a demo. You don't have it. If anyone has some sellotape or masking tape, even a Band-Aid if you're not bleeding too much. Anyway, I usually have overhead projectors. Nobody gives you overhead projectors these days, so if nobody gives me one, I'll just pretend. Oh! Band-Aid.
Yeah.
Thank you.
Unused.
Unused. Yep. Even better. So, Band-Aid. Wow. This is a waste of time. At this rate, I'm going to cut myself just opening this. Okay, so how do geckos do it? They're quite remarkable. They put their foot down. I have some videos, but I don't have time to show them, but I will show one. They put their foot down, and they stick very strongly to walls or ceilings, and then they can lift it up, all in 20 milliseconds. 10 milliseconds to grip, 10 milliseconds to come off. How do they do it? Anyone can have strong adhesion. That's not a problem. But to undo it very quickly, that's not easy. That's very difficult. Now, here's some detective work that you can all do. There's some... Oh, I'm pressing the wrong button. I'm sorry. So, notice three things which all sort of makes sense. One of them, you notice all the toes or fingers are radiating out in all directions. So not like ours, which are all pointing in one direction. Notice the funny body movement. The opposite limbs are always away from each other. And that's why when they move, they have this funny snake-like motion. But in particular, notice this. This looks very strange. How come these toes are bending upwards? If we look at our fingers, they bend that way. They don't bend the other way. So what's going on is as follows. And this is an example of what's known as frictional adhesion. Well, I don't know. Okay, I'm putting this thing here, right? And if I did it on an overhead, you know what you see. That. Now, if I want to remove it, I do that, and I really don't need very much force at all to do that. That's adhesion. Peeling. But let's say I wanted to remove it that way. I can pull as hard as I want, and if I pull very hard, this building will fall before anything else will happen. And, that's friction. Yet, once I've removed it this way or that way, the change in energy is the same. One is friction, one is adhesion. So, what does the gecko do? It brings down its toes. Imagine you're trying to pick up a beach ball in all directions, and then it grips. Now, if you try to lift the beach ball at that point, you wouldn't be able to. But it then pulls in. And now you get a very high friction. And then that high friction, when resolved in the direction of the feet and the body, gives rise to very high adhesion. Very quickly, by gripping. In order to undo, it peels backwards, just like I showed before, or just now, and that takes no energy at all. And that's the way the gecko does it, and I have a video of this, which is really nice. Here we are, it's already going. You see it lifting up its foot. This is a repeat. Each one is a repeat, down and up. A very unusual movement, but that's the way it goes from first strong adhesion and then back to low adhesion. But it makes a combination, it uses both friction and adhesion to do that. Oh, now where am I? This is always a problem. Does anyone know how to use computers? I'm sorry about this. You know what I'm going to do? I'm going to just start. I don't know what happened. I'll just go back to this. Oh, there it is. Okay. But then it's different from what I... Oh. Okay. I'm almost there. We have a gecko in my lab, and if you look at it, you think it's a dead gecko because that's the way you expect geckos to die. Actually, if you have geckos, you have to keep them in a cage, and you'll find they never spend any time on the ground. You know, they're used to being preyed on, and since they can go on walls and ceilings, then that's what they do. So if it's a glass cage, which is what we have, you'll find them on the wall or on the ceiling. And if you take a picture, that's the way it looks. If it looked the other way, that's when it's dead. But the important thing is to notice then these fingers in different directions. But also, as you go to higher and higher magnification, you find you've got all these things called cetal arrays and spatulas and things like that. These are just to increase the area of contact. But ultimately, the forces, it's just van der Waals forces, just simple forces that occur between all surfaces. Everybody was looking for some special type of force that was causing it. They thought, oh, is it like Velcro? But no, it works on molecularly smooth surfaces, so it can't be Velcro. Is it capillary forces? Well, it turned out it works under totally dry conditions. And it does it under all sort of almost all surfaces, except for things like Teflon surfaces or surfaces with, if you squirt oil on them, to which they won't be able to adhere. But luckily, they evolved not to be in caves made of Teflon. This sort of system works in other cases too. For example, the way muscles stick to surfaces, again, I have videos of this. You can see how they make them. They're very interesting. They make these threads and called the byssus and the plaque or the foot, and it's got this shape. And you can see that if you pull this way, the only way this can come off is by sliding inwards, and so you need to do friction to get it off. If you actually put tweezers here and peel it off, it peels off very easily. But as soon as you have this, you need friction. It's not suction so much as really a friction force here. So this is the way that animals also combine adhesion and friction. And finally, I just want to show a few things in a video or two. People only think of friction between solid surfaces, rubbing or sliding between each other, and maybe with a lubricant or liquid between them. But what about actually liquid that's actually is just moving along a surface? There's also friction there, because if you tilt a surface with a droplet on it, it's not going to slide down immediately. You need to get a certain angle. So what's going on there? Because here we can't use the same concept as before, because a liquid is so totally different from a solid. Because here, all the molecules here are actually not moving relative to the surface. It's only up here and on that side where things are changing. So quite a few people, including us, have been looking at things like what's known as advancing and receding contact angles. Advancing, if you have a syringe, if a drop advances, you get an angle that's bigger than on receding. You get the same effect in capillary bridges when you bring them together or separate them. Or even monolayers in contact. When you load and unload, as I already mentioned, you get a different adhesion coming in, going off. And it's interesting to know the process for that for liquids, and also its velocity dependence. And I don't have time to explain what's going on, except that if you have a drop moving, as I said, it's not like a solid moving bodily across. The molecules here aren't really changing. The molecules here aren't changing. All the action is here. These molecules are coming onto the surface, and by the time they reach here, they've restructured. And then when they go from here to there, they restructure as well. So all the action is here and here. This angle is always bigger than this. This is a consequence of the advancing gamma or W having to be bigger than the receding or retracting, as I said before. Otherwise, we'll have a perpetual motion machine. So there is a simple equation that one can derive. Oh, I'm not showing that equation because I have no time. But I will just show, and by showing you know, it's funny because I can't, what you see here is not what I see on my computer. I don't understand what's going on. Ah, here we are. So this is a drop just spread, being it works. Ça marche, as they say in somewhere else. But you see, coming back, you have a different contact angle. It's always smaller. Here, it's not very different because this surface is hydrophobic. Water doesn't have strong adhesion to hydrophobic surfaces, and therefore, the contact angle hysteresis is low. In other cases, it can be very high, and the last thing I'll show will be one. Oh, that's not this one. Now, this is something else, but here, all I want you to notice is that just as with solid surfaces, this is a different system, but what I want you to see is that you get stick-slip. Just as in the solid, even the liquid going on a surface can manifest stick-slip phenomena. So there's a lot of similarities in the way liquids move. And here, too, if you go to 0 velocity, there will be no contact angle hysteresis. But quite often, the velocity you need to go to is much less than angstroms a second. And that's why it's very difficult to measure. And that's an area that's been of great interest to many people and still is. So this brings me to the end of my talk. And that's my group taken a couple of years ago. I was just wondering if Bosun appears there. No, he'd already left the roost. But there is the final thing about the violins. So I have the answer to the violins. How many people think that the top violin is the top violin? We have a few. Now you're all being photographed, so who thinks it's the middle one? Who thinks it's the lower one? Oh. Well, it's the middle one. And most people did get it. And the reason being is that the main thing for a violin is to be able to have a sound at the extremes of frequencies, which this one has. This one doesn't, and this one definitely doesn't. And there's something about the Stradivarius violins that I don't understand, is that not only is it important to have a peak here, but also a gap here, and then another peak here. And how Stradivarius worked that out, I don't know. But anyway, thank you very much.
We have time for some questions.
So in all your kind of friction, it seems that you always assume there's water between the two surfaces. If you remove the water, is that crucial, or the effects are the same?
No, I showed some, right at the beginning, I showed some friction where there was no water, and then added water, and it made an enormous difference. Until damage occurred, and then it was the same. Because then the debris, the fact that there's water there, but there was debris, everything, it was now particles going over particles, the fact that there's water there didn't make a difference. It was all geometry dependent. But before that, the adhesion made the friction very high. In the other case, the water lubricated and the friction was very low.
Yes?
So in superconductors, in a magnetic field, there's a critical current that you need to have to depend the vortex status where you have ohmic dissipation. My question is, has there been cross-discussion between tribology and these problems in the context of depending currents in superconductors? Has there been a transfer of knowledge or ideas between the two fields?
No, unless the theory, unless the theory
mentioned this limiting case of zero velocity, which was, I forget, but it's something like a turn.
Right.
And then there are some analogous statements in the context of superconductivity.
Well, there are many theories in all sorts of other disciplines I see where at some point in some equation there is a sort of friction parameter which represents all mechanisms that could be dissipative. But can you ask me easier questions, please?
We'll have it ready.
Lawyer?
Maybe easier question. I was wondering if you put water on the surface for Gecko, do they slip down, or how water affects this friction adhesion? The thing doesn't work if it's water on the surface.
Right. First, let me say, if there's humidity, there is an effect. And interestingly, if the humidity goes up, the adhesion is stronger initially, and then it goes down. Because eventually it does act as a lubricant. But initially what happens, the water causes the proteins, the beta carotene or whatever proteins are there, to interact through hydrophobic groups. So now you can get strong hydrophobic adhesion. It depends on the time they're in contact. If you bring them into contact, and that's not only for geckos, and keep it down for a long time, the adhesion will slowly increase with time as water gets, it may not adhere initially, but with time it will, the adhesion will go up. And very often geckos will stay for a very long time motionless. And during that time, it's known that the adhesion is slowly increasing. And this is known for other systems too. So, but if it's totally in water, as far as I know, no. And in fact, they don't spend too much time in water, as far as I know.
This Fourier spectrum you showed for the earthquakes was slightly different than the other one on the slide. We had a fall off. Like
Hey, are you Melanie?
Yeah.
Hi.
Hi.
Okay, can you start again?
Okay, you had a plot of the Fourier spectrum of
Yes.
The earthquakes, and
Yes.
I noticed that it didn't follow the 1 over f squared curve.
Right.
It dropped off both at lower and higher
Yes.
frequencies. And I just wondered if there was an explanation for that.
No. I know that for sure, because I spoke to some of these people very recently at a Gordon Research Conference, and they say they don't even have an explanation why it follows the 1 over f squared, let alone why it doesn't follow the 1 over f squared. They have an equation which is totally empirical, but it's very similar to one in friction, which is not empirical. And that's where there's a merger of ideas coming in.
Any other questions? John?
Maybe charges and surfaces. You didn't speak about charges or their effect, because I guess it can also induce some stick if you have a patch, for instance, in a membrane, lipid membranes, you have charged lipids.
Right. Well, when you bring two surfaces together, there's always, if they're different, there's always charge transfer. And then there's a strong adhesion or additional adhesion due to there being a surface potential generated by the two surfaces coming into contact. And that increases the adhesion and the friction. And when you slide two surfaces together, if you measure the voltage of the current, you see lots of things going back and forth. So yes, there was a time when people thought that triboelectricity, which is what it's called, is actually the main cause of friction of dissimilar surfaces. But then it turns out that similar surfaces have usually a higher friction than dissimilar surfaces. But that is important, yeah. And that charge transfer and the forces it gives rise to is important as well. I don't know if I answered your question, but you can see fluctuations as you move surfaces, as charges go back and forth. If the surfaces are not molecularly smooth, then this asperity hits that, and then there's transfer, and then it gets away, then it jumps back the other way. There's been quite a lot of work on that.
That's it.
Has anyone looked at this stick-slip behavior of a liquid on a solid and a liquid on a liquid when you have the droplet being liquid crystalline, like a smectic liquid crystalline phase? I think this might be esoteric, but I would think the behavior would be very different if it was an ordered liquid as opposed to a disordered.
Yes, it's very complicated. Imagine you have two lattices, perfect smooth surfaces. You bring them together. They can be commensurate or incommensurate. Right. You take a liquid crystal, you put them between the surfaces. It will align, it will try to align to each surface. But once the film is thin enough, it has a problem if they're incommensurate. So there's a problem. You have a twist in the liquid crystal. You start sliding this surface, you find that the friction depends on the twist angle and the direction at which you're sliding, and the friction isn't in either direction, but it's in another direction. Have I answered your question?
Yeah.
People have studied it. It's very, very complex. And you can see why. Because at the molecular level, this surface is inducing epitaxially its structure on the liquid. This surface is imposing it. The film is thin enough that they have to somehow match. And now you're shearing it in yet a different direction, and the molecules then want to align that way. I actually have, with overheads, I have two transparencies which just have lots of dots. And they're identical dots. And I put one on top of the other so they're commensurate. Then I move them a little bit. And then everything gets funny, and then you can see, oh, there's all sorts of patterns that repeat themselves. And then I say, if I move this surface that way, which direction will the dots go? And it's amazing. You move it this way, the dots go that way. It's clear that these are very complex things. So there have been experiments done, but I'm not aware of any theoretical work. And actually, this could be very important in, often when you have reciprocating motion, like in a piston in a car, you always stop at some point. And it's the stopping where bad things can happen. But if the molecules force the surfaces to go in another direction, even though you're moving them this way, the surfaces actually start making a cycle, so they never stop, and you can reduce damage by playing these sort of things, patterning the surfaces and the molecules you put between them.
Well, thank you very much. These two principles of friction and adhesion are so ubiquitous in our world.
Yeah.
You must get a lot of questions, a lot of requests from people to solve their problems.
Yes.
Industry, particularly.
Yes, like I told you. And then I don't know if I've solved them or not. Sometimes they come back again and again. But eventually it stops, and then I don't know. Do they think I'm a nutcase, or I save them $100 million and they don't need me anymore? They never tell me.
Well, please join me in thanking Jacob for